So for part B of chapter 2, we have molecules that are three-dimensional. This spinning molecule over here, it's not flat. There's things that poke forward and poke back. And we use wedges and dashes to represent that when we're drawing molecules in organic chemistry. So if you see a dashed line, that is pointing back or away from the paper. So if you're looking at your paper flat, if you stuck your pencil out the back of it, this is pointing back. So we would use a dash to represent that. A solid wedge is out of the paper or forward. This OH group here is pointing forward. So you can see that the things that don't have rings, these will be pointing forward. This one is back. This is forward or up. This one is down. And we'll get into more of that later in the semester, but just so you're aware, we have things pointing forward and things pointing back. If I look at this molecule now, you can see these bonds are rotating just like in that little video. This orange atom is pointing forward and this green one would be pointing back. So we use the wedge to represent this one here and the dash to represent this one that's pointing back here. When we're drawing structures, sometimes we have pi bonds and sometimes we have to represent covalent bonds with resonance. Resonance structure is something that you're going to see a lot of in organic chemistry, so we want to be able to get a good understanding of it now. If you have this structure here, we know that there's a formal charge here. This is missing an electron pair. So we have 2 sigma bonds between carbons and 1 pi bond, and all of these actually are unhybridized p orbitals. That means that they can overlap. So all 3 of these are carbons that are sp2 or p orbitals. They all have these overlapping p orbitals that allow the electrons to move through the overlapping area at the same time. And that is resonance. So that means that all atoms must remain in the same place and only electrons are moved. We don't move bonds, we just move the pi bonds. So what I'm showing you here is the 3 carbons represented with the yellow C is there. And these are the p orbitals. What's hard to see here is the tracks here. So those are representing our p orbitals. So if you have a lone pair, this is showing our double bond. And this little train cannon car here is representing the double bond electrons. When you have resonance structure, these can move back and forth because our orbital was empty. If we put the electrons here, now this one over here is empty, and that is a resonance structure. All atoms must remain in the same place. Only electrons are moved. So we can move pi bond electrons or lone pair electrons. Because neither of the contributors exist, if we look at the MOs, which I won't make you do, we can look at average hybrids. So I'm going to go back one here. If we drew the resonance structure of this one, or if you look at those train tracks moved back and forth, this is essentially what we were drawing. So we've moved the pi electrons to a different bond that was having an empty orbital. So the average or hybrid is much more appropriate to use this. A resonance structure is a different representation of electrons that are spread over more than one location. So this electron pi bond here, those electrons can be spread across 3 different carbon atoms. So that's more than one location. And a resonance hybrid, which is also shown here with these dotted lines where these electrons are constantly moving back and forth, is not flipping back and forth like this, but it's an average of where the electrons are. If you think of a plum and then you think of a peach, you get a nectarine, and the nectarine is a hybrid of the plum and the peach. But when you're eating the nectarine, it's not like it is a plum one day and a peach another day. Or if you think of a puppy, you have a pug puppy and a beagle puppy, and if you breed those together, you get a puggle. But that puggle is not a pug one day and a beagle the next. It is an average of both of those things. Molecules with resonance are more stable. That way the electrons can be delocalized or spread over other molecules or carbon atoms so that it can spread the charge more easily. So the electrons exist in orbitals that span a greater distance, which minimizes that repulsion for the electrons. So electrons can spend time close to multiple nuclei all at one time, and that maximizes the attraction. So again, you have this resonance hybrid where the charge is spread out over multiple atoms. Charges can be delocalized. So the charge is spread out again over more than one atom, and it results in a partial charge as opposed to one actual formal charge. The way to represent resonance is that we use curved arrows, and that shows electron movement or electron pairs moving. Usually we start with a lone pair electron, and that starts at the tail. So this is your lone pair, or that's something that is partially negative. The arrow starts there and it moves to a partial positive or an actual positive charge. So here we have this electron lone pair moves here. That is shown there. And when you draw the result of that, these electrons have moved here. And then we need to put the positive charge here because we took the electrons out of this carbon bond and moved them into this one. So this is now no longer positive, but the positive has moved here. So drawing curved arrows or resonance structures is not something you can just remember for this chapter and then forget about it later. If you do that, it will come back to haunt you in several exams. So make sure you get a really good grasp on these rules. So the first rule is do not break single bonds in resonance structures. So we can only move bonds where there's electron deficient or where they can go. So we can't break any bonds. So you would not form this. So do not break any single bonds. You also don't want to exceed an octet for second row elements. So that means that this carbon already is making 4 bonds. We don't want to make it a Texas carbon by adding another electron lone pair in there and forming. All right, that is bad. Don't want nitrogen having more bonds than it needs. And then the same thing with oxygen. These things should not have more than an octet. So these are all bad arrows. Second row elements will rarely but sometimes have less than an octet. So you want to make sure that even though we're drawing resonance structures, that everybody is going to be a happy camper here. So you don't want to just give this lone pair onto the oxygen. This oxygen now has an octet, but carbon does not have an octet. That does happen sometimes, but it's rare. Charges in resonance contributors should be balanced. So if you started with, I'll use this example again here. This is the resonance structure. Notice that the positive charge, or the charge was positive here before, and the charge is still positive. So the charges should be balanced. So you can't start with no charge and end with a +2, etc. If we're going to use these rules, draw resonance structures for the two below. Here is an empty orbital, and I can draw electrons from here into that. And this double-headed arrow represents a resonance structure. That is the main carbon skeleton, which I have not changed any things there. And the electrons have gone here, and then the positive charge moves to the carbon where I took the electrons out. One thing that you would not want to do is move the electrons to here. To form this, because this is an sp3 carbon and you would be exceeding the octet, so we don't want to put carbons there. So this is a no-no. You also don't want to break a bond and put electrons here. So there's lots of things wrong here, but mostly you're breaking that single bond and you don't want to do that either. The best resonance structure is the top one here where you move the pi electrons into the empty orbital. For this structure here, what you want to do is move these electrons to form that double bond. And these electrons, even though there's no empty orbital here, this is an sp3, this is also sp3, so we can't put electrons there. We can put them onto that carbon. So the skeleton stays the same, and my electrons go here, and then now I have that extra electron pair here, and you want to make sure you put the formal charge there. So that is a resonance structure. It started out as a negative charge, and there's still a negative charge here. So our charges are balanced. Carbon has the octet, oxygen has the octet. We haven't broken any single bonds, so that is one valid resonance structure. We would not be able to move electrons on into there. So you wouldn't want this because again, that is an sp3 carbon. That would exceed the octet. So resonance structures have seen already that they have charges. You want to make sure you include them. It's absolutely critical that you include them. So if we draw the resonance structure here, the result of this one, so the carbon skeleton stays the same. And if I follow the arrows, these electrons come here to form the double bond, and this goes onto here, and we include the negative charge because that carbon has an extra pair of electrons. Now before oxygen was neutral, the whole molecule was neutral, and now I have a negative charge. But oxygen was making 2 bonds before, now it's making 3, so this needs to become positive. And if I follow these, if I follow the arrows here, this is the same. Just drawing in my carbon skeleton. We have electrons that go here. These went here. And oxygen got an extra lone pair. So this one is negative. This one is the same, negative. Nitrogen still has 4 bonds, so that is positive. So this started out neutral, and then I have right now a -1 overall charge, so I need to fix something. Electrons were taken out of here, so this is now positive, so now I have an overall neutral charge. There are several patterns that we'll see when we're drawing resonance structures. One is an allylic lone pair, or a lone pair that's next to a pi bond. Vinylic is the position that is on the carbon double bond. The allylic are the ones that are next to the carbon double bond. This is also an allylic position here. That one is not. So this is allylic because it is on the atom next to the double bond. This is not. If you have this situation, usually you end up drawing 2 arrows for this. So if I'm going to draw a resonance structure here, this goes here, these go there, these can go down here. So in all these, I'm drawing 2 arrows. So you just want to look to see where the hetero atoms are that can hold an extra electron pair, or where you have p orbitals. If I draw the result of these, the electron pairs went here, negative charge, and there's a positive charge on that oxygen because oxygen's now making 3 bonds. So here the oxygen's making 1 bond, so it will have a negative formal charge. And there's a double bond here, this will be positive. This one will have the double bond here. This will get an extra lone pair, so that's negative. And then I have a double bond here and extra lone pair on the oxygen. And nitrogen is positive. So all of those involve 2 arrows. So that's the allylic pair of lone electrons. We can also draw resonance for allylic carbocations. So before it was a negative pair, this is a carbocation version. So it's a positive charge next to that carbon on the double bond. So I follow the electrons. The electrons moved over here, so the positive charge is now here. This usually involves 1 arrow. So here I can draw 1 arrow to there. That one is different. So the positive charge is where I took it out of. And that one is still there. You can also draw an arrow to this one. And that goes there. So again, these all involve 1 arrow. So if you have multiple double bonds, you're going to have multiple contributors. You can have a lone pair adjacent to a carbon. So if I draw the result of those, these electrons move down. These ones go over here. And now this is positively charged. This one's involve 1 arrow as well. You can have pi bonds between 2 atoms of differing electronegativity. So for this, you can drop these electrons here. And I know this was one of the examples where it doesn't happen often, but it can happen. Same thing here. And oxygen and nitrogen, because they have lone pairs, are capable of taking on an extra lone pair. You can move electrons around a conjugated pi system or in an enclosed ring. So I can move these. So if these went here, here, and here. So you can keep pushing those arrows around the ring. So just to sum up, for an allylic lone pair, you end up drawing 2 curved arrows. Allylic carbocations have 1. Lone pair adjacent to carbocation has 1 arrow. The 2 different ones here have 1 arrow, and this one has 3 curved arrows. So go ahead and try to draw resonance structures for each of these following compounds. This one has 2, if you can come up with 2, and this one has 4. So for this first structure, you can use this pi bond between 2 atoms of different electronegativity. So I move those electrons from the pi bond onto the oxygen to give us the O negative here. Since I took the electrons out of that carbon, it's now positive. And then you can draw another structure with these pi bonds moving into this one, and that leaves that positive. The oxygen is still negative. This one's kind of tricky because we had that benzene ring, so that adds a lot more arrows that you can draw. So I'm going to move this electron pair to form a double bond. Once it does that, these have to go somewhere, so I'm just going to put them onto that carbon. So this is negative on this carbon right here. We can also move those electrons into here and put that onto that carbon. So the double bond forms here. There's a negative there. And then these electrons can come in to form a double bond here. Those ones go onto that carbon. You can draw these electrons back into here, and those will go on to the oxygen. Then we get that one there. So those are the 4 resonance structures you can draw on that one. Not all resonance structures are created equal. Some are more likely than others. Just like puggle puppies are not perfectly 50-50 mixed, there's different percentages there. It's the same thing with resonance structures. So the most significant resonance forms have the greatest number of filled octets. This is going to be the minor contributor. This is the major because we have octets here and here, versus this is empty. That one has an octet, but that one's empty. Again, here, this is going to be the major contributor. We have full octets here. This one is deficient. And then this one is insignificant because you have 2 really unhappy atoms. This one is miserable. An oxygen with 2 lone pairs and 1 bond is not a happy camper. For structures with fewer formal charges is more significant. So this is the major. This is minor. This is in the medium category. So here we have no overall charge. Here is 2. This one has 2, but nitrogen is happier to carry the positive charge over carbon here. And then here, this is delocalized negative charge. The oxygen and the carbon are sharing the negative charge, so these 2 are major contributors. This one's insignificant. Carbon doesn't want to be negative, while oxygen's negative and the other carbon is positive. And then the structure with a negative charge on the more electronegative element will be more significant. So this is a major. Oxygen would rather carry the negative charge over carbon. And nitrogen would rather carry the positive charge over oxygen. So nitrogen, because it is less electronegative, will be better at holding the positive charge over oxygen. So this is minor. Resonance forms that have equally good Lewis structures are described as equivalent and contribute equally to the resonance hybrid. So these are all equal contributors because they're all good. This one is terrible. So here nobody is happy. Everybody has a charge. In any of these, carbon has 0 charge, and the oxygens are rotating the negative charges all around there. A resonance hybrid is a combination of individual resonance structures. So we saw this a little bit earlier. The resonance structures here, if you draw the arrow, the hybrid is the dotted line version of it, where the positive charge that was here and here is spread out over those carbons. So it's being able to spread it over 3 atoms instead of just sharing it on one. So a resonance hybrid can be drawn with the partial bonds and partial charges to show the delocalized electrons. Draw a resonance hybrid for the following anion. First, you draw the significant resonance structures. These electrons can go here and those onto there. So that is one resonance structure. And then determine the relative significance of each. So between these two, which one is more relative? Well, this one is more significant. So this oxygen is better at holding the negative charge versus the carbon holding the negative charge. So this is going to be the more significant one. And then we draw the average with partial charge. So we have oxygen and our dotted lines. This is partially negative, partially negative. Draw a resonance hybrid of this structure. So we're going to start with drawing the resonance structures. We can move an electron pair here. So our negative charge is there. We have a pi bond here. That one was there already. You can also draw the one going this way. So electrons here. These are both significant. The oxygens actually would rather carry the negative charge over the carbon. So we can draw the hybrid of these. So our dotted lines go here. Our partial charges will be here. And also on this carbon right here, which is where it started with. So this would be the resonance hybrid for those.